Okay, I want to introduce Dr. Sue Hovorka.
An hour?
Sue's a sediment ecologist who works on fluid flow and diverse applications to it, including water resource protection, oil production, and waste storage. She's led a team working on geologic storage of CO2 since 1998, with a focus on field studies, monitoring, and capacity estimation. Projects include saline injection at the Creel test site at Cranfield, Beal, and EOR, at the Sackrock oil field, Cranfield, Hastings, and West Ranch Industrial CO2 utilization project, and the Go-In-Car offshore characterization studies. She specializes in monitoring to document potential. The Gulf Coast Carbon Center is leading efforts to develop offshore storage capacity in the U.S. and globally. She has a long-term commitment to public and educational outreach with a BA from Irwin College and a PhD in geology from good old University of Texas. So without further ado, Sue.
So I wonder how I should talk to you. How many of you know a lot about CCS? How many of you have heard of it? Okay, so most of you are in the. Okay, that's good. I'll start there. And what my motivation here is for you to know is, as members of the citizens, we have certain obligations to know how we should deal with climate change and the related policy problems. So I would like, and especially as geoscientists, most of you are geoscientists, right? So as geoscientists, we know stuff that our neighbors don't know. So what I want to arm you with is some information as one geoscience to another that you could talk to people about what we know about the subsurface, what we have confidence in that they may not have confidence in. That's my motivation here, is to let you have enough information so you can have an intelligent conversation based on your geoscience background. Now, some of you may work for somebody who actually wants to take more aggressive action, and I won't target my talks toward that. We are working, that's why I'm late, as we're talking about with multiple landowners and industries, of wide portfolio of industries, including ones that are familiar to us as geoscientists, like Marathon. We're talking to Marathon about what they might do or might not do. But they also include gas handlers like Air Products or LNG handlers. They also include investors who have a carbon burden, so like Google and Microsoft or shopping people who want to decarbonize their product lines. So we're talking to a wide array. More loud. I could also hold it up. How's this? Any better? Oh, okay. Thank you, Charlie. All right. So, see, greenhouse gases, where do they come from? Here's a graph. I thought it was kind of cool, of all the sources of greenhouse gas. And you see that there are three big ones that we have. I'll give you my slides if you write me. You're welcome to them all. We have sources of greenhouse gas from the transportation, from stationary sources, and from other generating electricity from industrial sources. We also have a number of other sources of greenhouse gases. Natural, of course, there are natural sources that aren't in here. There are releases from CO2 from lakes, for example. The other part that's not shown here is, so what? CO2 is very busy in Earth systems. CO2 drives weathering. We turn mafic minerals into calcite especially at spreading centers of ridges or on weathering on land. So there's lots of abatement for this CO2. CO2 is taken down by biologic systems through photosynthesis and put on the base in the ocean, where as carbonate, as organics turned into buried products and the ocean floor and turned into soils and kept in timber and on land. So lots of pull down. What we see though what I'm sure you've seen before is that this the effectiveness of us as geoscientists in extracting carbon from the earth has exceeded the ability of natural systems to take it down. So we need to use our skills as geoscientists to offset what we're doing in pulling CO2 carbon out of the earth in fossil fuels and moving it directly into the atmosphere. The atmospheric and ocean systems can't keep up. We could talk about this more. It's not my specialty though, and I only know what I read in the newspaper about climate change. You could ask me about that, but we can discuss it, but I don't know much. So I'm talking about this diagram, which is an old diagram. I like it for its simplicity. See, it started back in now at the time of drawing was like before 2010, saying if we have more people getting more affluent on Earth and using fossil fuel as they have in the past, the amount of CO2 in the atmosphere will go up with uncertain and potentially extremely negative consequences. So in order to stabilize it or bring it down, you need to do a lot of things. And people often say, biggest criticism of what I do CCS is say, well, why aren't you doing something other than that? And the answer is, oh yeah, we should do that. But as a geoscientist, I have skills to contribute in the one domain. So this is my slide to say I respect my brethren, all the other people who are using other techniques to bring CO2 down. We're all needed, and I'm dead serious about that. So I could talk about my friends who do other things, although again, it's not my specialty. With the UN report of a year back, 2 years back now, realizing that we want to go on beyond this triangle and actually reverse some of the trends to pull, we're going to have a so-called overshoot of the safe limits, and we want to pull CO2 down. So there's increased emphasis on technologies that can pull CO2 down. And there's beginning to be a lot of investment from a lot of different entities who are announcing investment needs. So the whole interest is going up. What I point out to you here is the stuff I'm going to talk about, which is CCS, isn't a bunch of them, not all of them. It supports a bunch of them. So this is an underpinning technology for many things. So here's the palisade of sources. The height of the bar and the redder colors are larger emissions. So you see the palisade along the Texas coast is one of the largest on Earth. Another one is up in the Ohio Valley. They have a lot of coal-fired power plant, heavy industry up there. But in the Gulf Coast, it's superimposed on the thick subsurface. So the problem and the opportunity are coincident here. So what is storage, geologic storage? What are we talking about here? Right now we're extracting carbon from storage in the earth in geologic settings as oil, gas, coal, and combusting it. And currently we're emitting essentially all of it to atmosphere very efficiently, very well, and taking a lot of energy, which is very important, off of it. So if we don't want to do this, and we don't, some people say we have to get rid of the whole thing, but we're going to talk about here a mitigation for this process, which is part of the equation for many things. So to reduce the emissions from point source, you can capture it, and we can talk about the capture techniques. And if you want to swing by, we have a pilot plant out here that belongs to Gary Rochelle where we do capture. So I could chat about capture methods, but I'm not an expert in capture either. I'm a hobbyist. It's shipped as a dense fluid, so-called supercritical. So it's high density, liquid-like compressibility, gas-like viscosity, selected via a pipeline usually, or maybe a ship, to a selected and permitted injection site. So we can't do it here in Austin because we couldn't get a permit, and I'll tell you, because we don't have a deep enough sedimentary wedge. CO2 is injected at pressures into pore space, at depths below, isolated from potable water in the atmosphere. So that's why when people say sequestration, they mean isolation in the same way that a jury is sequestered from the media. So it isn't storage unless it's stored, right? A storage cabinet is something that keeps things stored. So storage is implicit in this, and we have to use our skills as geologists to show that the storage is going to be effective. And I'd love to talk about that. And it's stored in the pore spaces over geologically exclusive time frames. We're not using caverns here. We're not using, because the volumetrics don't match the need. So we're using the pore spaces because the total volume of pore space is large enough to put a major dent in the emissions. Right, so that's the basics. Where this is a brand new map of it's. We look at the what's a target, and you see the storage injection zone has to be below fresh water and deep enough so the CO2 is in the denser phases, and above the basement or overpressure. So there's a window of depths that are suitable, and we want sedimentary rocks because we want that overburden and confining zone. So we need the layering of sedimentary rocks. They can be structurally complex, but they need to be layered. So we can't inject effectively into rocks that aren't layered. Because they don't have the KVKH, you don't have a vertical anisotropy to provide the needed retention confidence. And the colors, the blue colors show where in the U.S. can do it. The U.S. is very well endowed compared to the world. And notice that the Gulf Coast is extremely well endowed. Here's the global equivalent. This is the storage window. Approximately, the hot colors have sedimentary rocks of approximate reasonable thickness. The gray areas are losers. Notice that there are places on Earth that geologic storage is not, as we understand it now, is not available. There's some other things we could talk about, mineral storage, for example, if you wanted to, but it's not in my discussion today because it doesn't do very large volumes today. So Gulf Coast, this is work that Tip Meckel has been doing, looking at the coincidence of many things. This is a more detailed version of the skyscraper cartoon I showed you before. So the sources are in blue dots. The pipelines are in yellow and blue. So we have available, this is our existing CO2 pipeline in yellow and hydrogen pipelines in blue. So we have a lot of experience and skills in pipeline building and handling. The green areas are some of the available seismic. So we have a lot of information about the subsurface. If we put the wells on here, the well density is incredible. So we could talk more about wells too. And both the onshore and the offshore are in consideration and some of this belongs to the public, both the offshore and state onshore waters, which is interesting because they're already jointly owned. So this is what CO2 looks like underground. This is an image from 3 kilometers depth from a project we did in Mississippi, and it's collected by electrical resistance tomography. The hot colors are the CO2, the image of the CO2 plume that we developed and monitored over time. It's a time-lapse signal. I'll tell you more if you want, but I just put it up here just so you could. Okay, so here, I showed you the cartoon, and this is what an image is like. This is the plume of CO2 moving from an injection well into the channel system. In fact, you're seeing it. The hot spot is a channel system with high transmissivity. And we need to tell people that we can make pictures like this. You know, that y'all have done a version of this kind of picture of what the distribution of fluids is on the subsurface. People think that's dark magic, that we can't do anything credible. Partly we express some uncertainty when we do that. We have some confidence that we're right, and we have some uncertainty. People feel that uncertainty is maybe unacceptable. So one of the important things we need to do as geoscientists is communicate that we do know what we're doing, and that we can make reasonable guesses. And one part of the reason you can trust us is because we can express that our confidence in our ability to describe and map the rocks and the fluids in the subsurface. People think that it's highly unlikely that we could know what's going on down there. But of course, you guys could probably draw a picture, right? Right down what's down there. I mean, so this is my key point. I put it here. So if you take a nap now, this is the thing I think the most important. I told you what CCS is, and the most important thing that we need to take forward from this is talk as geoscientists about our confidence in the subsurface. Let me give you some information about that confidence now. The things we want to tell people are the nature of sedimentary rocks, that they have pores in them. Many people think rocks are tombstones. They think rocks, if you poured water on it, the fluids couldn't go into a rock, could they? So a finance person thinks rocks are solid. Tell them rocks have holes, and that's what we're talking about, is the behavior of those holes. Yes, fluids go into rocks. We know quite a lot about this. It's something we learn in school. And the geometry of those layers that will accept fluids and how they interact with the fluids is something that's a mature science. So people think that a fault, if you ask your grandmother, she'll say, whose fault? So we need to say a fault is a barrier to flow. It could also be a conduit. We understand it. We have our tools. We can understand this, the other thing about the nature of faults. It's not a bad thing. It's a thing. All faults don't cause earthquakes. All this kind of basic information that all geotechnical people know needs to be communicated to people who are trying to make decisions about mitigation of climate issues. And the performance of wells, we know how many of you have dealt with wells in some domain? Yeah, so usually they're good things. We can move the fluids in and out, but sometimes they have plumbing problems, and the plumbing problems are plumbing problems. They're not unassailable. They use very large, expensive wrenches to solve these problems. So this is a little bit of the detailed knowledge and how it applies. So I'll talk a little bit more about what's at the cutting edge. We know a lot about what makes a good storage reservoir that traps hydrocarbons. Storage for CO2 is less demanding. We don't require a source for hydrocarbons. CO2, we're going to place the CO2 in there. Also, hydrocarbons are huge, huge volumes, and they keep going for geologic times. For storage, we're going to place them over decades, not geologic time. We're going to place them and then stop and move someplace else. So we're not going to overtax the system, so that we don't have to have as good a trap, as good a storage container to assure storage. You just because you can stop before you overfill it, which is an interesting new idea that we've been exploring a lot. So we don't need to only use the places that trap hydrocarbons. We can broaden our search parameters and say if we stop short of X million tons, it will all be retained. If we overfill it or overstress the column height, it will not be retained as effectively. The second thing about models is people think that either models are very unlikely to tell us anything because they don't trust a model, or they trust a model completely. And the answer is no. We use the models as an experimental tool. So we use the models to say what we think is going to happen, and then we test them and say, if we're wrong about this, how would we know? What would be the implication? Say, well, we better find out if that's true. Yes, if we've got thief zones that are going to make the CO2 move rapidly in this direction, or all the CO2 is going to go into one narrow zone, or we have a high state of stress that might cause geomechanical, it might cause felt seismicity. These kind of things we can know about and put them into a model and know at what level of uncertainty would cause risk to people. So the fact that we do models doesn't mean we have a single right answer. It means we have a tool to probe our uncertainty and tell people what's critical that we need to know. And that's a good model. And I work a lot on targeted improvements in monitoring to know what the areas of remaining uncertainty, how we reduce them during injection. So the deep subsurface and the near surface, I'll talk a little bit of detail about what we do for monitoring. For some of you who work for consultancies, does anybody work for consultants who's interested in CCS maybe? Anyway, I'll give you a little, we have some nice, you're welcome to come back to us for more technical information. We spent your tax dollars to get a good bit of information about best ways to image and CO2, to monitor it, to know whether it's behaving correctly, know it's leaking, and we're glad to hand out papers and so forth to people who are trying to take this into commerciality. So injection is into on our T-shirts it says the permanence is in the petrophysics, meaning that we're talking about two-phase flow in porous media. Your average oil field, how much of the oil will come out? Can you get out possibly? Anybody know? Right. The amount of so people, when finance people call and say, well, all the CO2 might come out, and I say, no, we can't get it out when we try. It's because of its behavior in a porous system. The capillary forces dominate this two-phase system. So our experience with oil and gas retention is very useful. I said it was easier than oil and gas. We're not going to pump it. We want it to be retained so that it can't come out under buoyancy forces or under injection pressure. But the driving force, we're not going to pump it. So most oil fields are even penetrated with wells are sufficient traps. We just need to find the ones where the driving force is sufficient to make it move out. Okay, so here's some images that my colleague Sahar Bakshian made. The yellow one is a CT scan of the pore space, and the blue one is a fluid flow model of the CO2 accessing the pore space, and this is millimeter-sized ball looking at this pore space. Something to communicate to people is that, yeah, porous media accept fluids, and their behavior is really well known. It's very important for our confidence in permanence of storage. So here we are trying to get this quantitatively. This is a micro model. Let's have a scale. Yeah. So it's a glass slide engineered, making micro models with the silicon wafers to inject fluids so we can look at the water. SW is the water saturation, how much water you can't get out by bubbling CO2 through it. So and looking at the impact of heterogeneity. You notice this fine grained layer won't let the gas in because of the capillary forces. The water saturation is 56%. You can't move CO2 very well through that layer. So I said layered rocks were really important to assuring the permanence that we talked about, and this is why. What we do in our experiments these days is drive everything to failure, which I think would make UT can't do this right. All of their experiments are failing. No, we drive them all to failure, and that's because they let us know when to stop. I said the confidence here is we're not going to let the injection go over. We're not going to overwater the flower pot so that they spill. We're going to put the amount of water that the flower pot can hold, and then we're going to stop. So our job is, as people who work up the site characterization and the modeling, is to decide how to stop, how much is too much. Another thing we do is look at the flow in a controlled environment. This is a dark room that's right over here on campus. If you had more time, you could go. It's got a sandbox that's a centimeter or two thick, and it's packed with sand in bed forms. You see the bed forms, and we inject a proxy, the orange proxy for CO2, into it, and watch how the layering and the bed forms trap the CO2, and image it over time. So here's a couple images of the bright colors are the CO2 proxy being trapped, and we're experimenting with how long a permeability contrast needs to be. So there's some very short curved ones, some intermediate length ones, and some very long ones. The longer, the more they trap, but you notice the short ones even trap a lot, and we add them up and to see what's sufficient to provide the retardation. And again, we drive them to failure and decide how much injection, with injection capacity, seal capacity, how much could be held back by the seal. We have a new idea called composite confining system, where we're trying to qualify exactly how much is needed to provide assurance that storage will be successful. In doing radical things, we're injecting off the structure. Why? Because it keeps the column height low, and because it avoids the penetrations. Every penetration in Texas and Louisiana, every structure in Texas and Louisiana has penetrations in it. Some of them are very old and suspicious. I never like wells that are older than myself. So we are injecting into zones, and here at the top one we see this is an experiment, a model experiment by one of our students, injecting in the syncline versus injecting in the anticline, and the syncline spreads out, but also it doesn't flow vertically as much, and it's retained by those capillary forces very effectively, and it avoids the penetrations, the wells on the crest of the anticline and the structure and the complexity of the structure, and avoids putting a strong driving force. So it's a new radical idea that we love synclines. I never got to study them in school, but they're fun. So here's some injecting in synclines between faults. We put the CO2 plumes in the synclines between the faults. And then we have an area of elevated pressure, and that's very important because paper we're working on today is about pressure space. The commodity of value is the space that you have to put something into. So just like storage, you want to know how many cubic meters of storage you have. It's important for geologic storage that it's already got a fluid in it, and you have to be able to displace that fluid. So where's the stuff that's in your storage space going? Figure that out, and then you know how much storage you have. This is an obvious idea, right? But it's not so widely, so it's a new idea we're working on here. So if you're developing it commercially for somebody, come talk to us about pressure space, which are our new buzz for today. So I told you some things nobody else knows, even though we just started talking about this topic. Are those new things? Yeah, they're new things. So these are a bunch of the experiments we've done in the past. So there are 5 locations and 7 experiments in 5 locations that we published extensively on. We've also done quite a few that are more commercial and we can't necessarily talk about today, but that are more in the planning stages too. So we have another dozen experiences that are that give us breadth. We also work a lot internationally and get to go see what the best experiences the Australians are, which is really enriching. There's some great stuff going on globally that we can lean on and learn from. So what could go, now I'm going to talk about what could go wrong, because that's what everybody wants to talk about, right? I talked about what could go right, and I told you about our confidence in as geologists in predicting things and how bedded rocks can retain. So I talked about that. So now we're going to talk for a little while about wrongness. Because people like disasters much better than security. So the worst thing is here. This is a Crystal Geyser in Utah. Somebody long ago drilled a well and it didn't work. They didn't hit anything. They got a geyser. It squirts CO2 intermittently. It's a cold geyser, so it builds up CO2 and then it blasts it off. People go swimming in it, so it's not a huge calamity, and it's in an area that's charged with CO2 that has lots of natural CO2 springs. I've never had a 4-wheel drive vehicle tough enough to get out here, but if you ever have a chance to go out in the Green River and see the Crystal Geyser, let me know. But we worry about this in someplace not in Crystal Geyser or Utah. We worry about wells, say old wells that are near somebody's facility or house. And old well leakage has been the problem of most. Well, old wells are a recurrent problem. If you want to read about them, you can Google Railroad Commission. That's the regulator for wells, oil and gas wells in Texas. Blowouts. So Railroad Commission blowouts, and you can read about problems with old wells. So there's dozens, not thousands, dozens of problems with wells. Most of them are rather modest. Some of them are somewhat, cost $500,000 to clean up. $500,000 is not a lot for deep subsurface work, but it's chump change. You have to fix them. So wells are supposed to be constructed to be isolating, and most of them are, but there are some fraction that are not, and the fraction depends on things. So you need to find out how good the wells are in order to have a storage site that is secure. So the number one top things is the engineered features, which is tragic for us as geoscientists, because I would rather the failure be, something I'm really interested in. But well behavior is the likely failure scenario, and it's the engineered system where you put the cement behind the pipe, and then to plug the pipe itself during the plug and abandon. So you're supposed to isolate the well, and the failure of the intended isolation is the major failure reason. Part of the reason this failure happens is because it's designed for production concept. So a well is mostly designed to either produce oil or gas or water, and it's got a cone of depression, and you're talking about inverting the energy so that you're adding more pressure to it and you're taking it out of what its design parameters, which is why we struggle with it. So this is not unsolvable at all, but it's a thing, and some of the things we're proposing more research on is fastest, easiest ways to provide highest levels of confidence that existing wells in the system are correctly isolating. Here's some examples of things going wrong. This is Aliso Canyon. This is Google the amount of money that the operator, who's I can't remember now, California gas company. So you see that black, can you see it? The black thing that's coming up. The well was not completed correctly. They got an exemption from all those safety rules. I could tell you more about it if you wanted. And it's into a gas storage, not a methane storage, not a CO2 storage. But the methane leaked. You can image the methane with infrared, so they flew over it with drones with infrared camera, and then image this black plume coming up. It's not, you can't actually see the black, that's black and infrared, but if you use the right wavelength, you see the black plume. It was a hazard to people living in the dense suburbs down at the bottom of the hill and so forth. Bad disaster, we have to not let this happen in more places. It's not acceptable. They did stuff that they shouldn't have done, though. So it's not like this is going to irremediable. This was a human error that the operator and the regulator together wrote down a decision which was a bad decision. So what do we do to avoid this? What we propose is using monitoring in a shallower zone to do surveillance to see that no fluids are escaping out of the zone. So you have an injection zone that's supposed to have elevated pressure. See the black line? As we inject, the pressure is supposed to go up. Now we want to know that this well and all its sister wells in the field are not leaking. So they're supposed to stay flat, right? The injection zones should have the pressure. The above zone, that labeled ASME above zone monitoring interval, should not be hydrologically connected. If you see them being hydrologically connected in the pressure response, well, get out there, you got a problem. So it's a very straightforward thing that we can do. It's not that there can never be a problem, but we do have very simple things to do to avoid the problem. So here's me making more problems. What if the plume goes something you're not supposed to go? And I said, we always fail this. So this is a very simple tank model where there's two plexiglass plates, and I'm charging them with lamp oil here. In the center is a well with lamp oil. And I thought I was going to play around with the red and the blue, but what I did is let the red, I guessed wrong about how much red I could put in, and it came out and started bubbling out at the edge. So we create these failures, and then we say, what do we do to avoid this failure? How could I have kept from bubbling it out? And the answer I would have paused in the red and seen how it was moving, and if it was moving out too fast, I would have known I couldn't inject blue behind it. It's in a ice chest, so the failure wasn't serious. We make our failures in the lab and avoid them in nature. So here's one people talk about all the time. This is a volcanic lake, Lake Nyos, and it killed lots of people who lived on the lake shore. But this was not an analogy for a CO2 storage site. Why? Well, it's a volcanic terrain. Remember, we're not working there. It's a deep lake, and it had dissolved in CO2 at the bottom, and it was deep enough so that it stratified, and a landslide or something caused the lake to overturn and release the CO2 and other gases all at once, and they ran out of the basin and went down in the valley and killed people. So CO2 can kill you. Here's an example. But this was not a storage site. There are many reasons why a storage site would stop short of being this level of disaster. Starting with, we wouldn't put it in a volcanic crater. And proceeding on from there. And we wouldn't put it in a deep lake. And we would watch out for environments that could be hazardous, like basements, for example, are hazardous for CO2. So the number of basements in the Gulf Coast is small, so, but we need to be alert to them. Okay, so what do we do for monitoring? We used to talk about monitoring everything, and I have to say, I have sinned. I have monitored everything, gone out with teams and put as many gizmos as possible, made friends with, it was very popular to let people, all kind of people come monitor at the projects we were doing. And it was really, really fun. But it's not what we need to do commercially. We sampled the water, we put in tracers, we had fun in the lab, so the new way of thinking that I'm talking about that's catching some traction, you're going to monitor systematically to reduce risk, and you're only going to monitor those things that have real consequences for the success of the project, in terms of storing the CO2 and assuring that no harm occurs to the human or ecosystems. So we're not worried about predictions unless they're consequential. So you really focus in on the consequences to the project's success. We use geotechnical approaches. We're not talking about over-engineering it. We're looking for indicators that we know as people who look at the Earth system. So here's a workflow. I won't go through it, but if you want, it starts at the top with assessing the risk, and it comes out at the bottom to report that we systematically limited the things that can't happen, which we call material impacts. An impact is something that happened. A material impact is something that was consequential, mattered. So we're looking for the things that matter. We're systematically going through a scientific method-based hypothesis and then a measurement set of measurements to determine whether the we think that our intuition is that this is not likely to occur. We picked this site, but we or somebody else said it might happen, so we systematically set up the hypothesis that this is happening. So I gave you an example of there was a thief zone that took the CO2 rapidly, laterally. So how can we measure that? We could measure an injection profile and see if all the CO2 is going in one zone, or we could monitor we could image the plume, see if it's all the plume or the pressure, and see if the pressure or the plume are in one zone preferentially, which has happened. And then if that's not since our system could catch that, we will know that it's not happening. If it is happening, we'll know in time to correct it. So a lot of interest in monitoring groundwater because it's the protected resource. The permitting process from the Safe Drinking Water Act is for safe drinking water, and that's what controls the U.S.'s underground injection control, UIC program, is protection of, the jargon is USDW, underground sources of drinking water. So this is, you can tell by the jargon that this is a mature protected resource. So what information is needed? We start with an idea of we've done contaminated site approaches. Who thinks we should use that? No, don't use that. Why? Because the contaminated sites have something distinctive that's toxic or carcinogenic or something, right? And it's not supposed to be there. So if you have lead, you measure lead or arsenic or something because it's unique and not supposed to be there. CO2 is everywhere. So you can't start by measuring CO2. It's going to lead you down the garden path. What you have to do is look for signal that would tell you if in case there's an incident, something happened, you had an engineering failure of some sort, problem with the well, or an allegation, which is even more likely that one of the neighbors complained and said, usually they tell me that there have been snakes. So we've had an awful lot of snakes ever since you've been working out here. So whatever the neighbors are concerned, and you want to know, is it the project that caused this, and is there a consequence? So you would tailor our monitoring not like a contaminated site, but in order so that when we see a signal, we can figure out if it's us, and only if it's us. So here how we do it. Here's a groundwater scheme. We put CO2 into the groundwater. We pump out some groundwater and we put CO2 in it. And we push it back in the groundwater and see what happens and publish it. And this lets us figure out what is the signal of CO2 interacting with the rock. It's very subtle. It's very hard to find, and can't get it very far from the injection well, or from the leakage point well, which is great news because it means that the impacts are very local, very limited, very local. We do this at Balcones Field Lab, and we work at the scale of like a meter. We can detect a leak a meter away remotely. So not everything is this benign. Here's some dry natural leaks in Europe at volcanic centers, and here's another one, volcanic centers at Mammoth Mountain. These are very large gas leaks. And so we can gain some information about those too. We do a lot of work with students and graduate research assistants. So here's one of our students presenting for Indonesia, which I'm proud of. And we'll have a new crop coming from Indonesia and Indonesia and Nigeria, and so we've got Mexico and some American-born people too. So we have a big crew of students coming in, and we do a lot of work coming here to teach people. So this is my teammates. They're not to blame for what I said, but if you want to talk to them, they're very, very good. There's our web address and our collaborators and our sponsors that let me come